Welcome everybody to our high altitude balloon mission with NASA Goddard support workshop number 2. And we have a really short agenda. We're going to recap the dates and the deadlines, and then we'll have our support Q&A session, as well as our next steps. So here we are. This week is workshop 2 of this week of the 20th of May. And then from here on, it's all about building the payload. You test your own payloads on site before you send them off for us to test them and for integration. And Jim, off to you to take Route 66 off to New Mexico. And so, yeah, with our support session, let's see, does anybody have any questions? Has anybody had any challenges?
Bridget's been working hard on soldering. She's got all the wires soldered, and Bjerker has approved her plan before that. So she was so excited. She had planned it out properly and did everything she was supposed to. And then it took a little while for her to get the hang of soldering the wires through, but then we figured that out. She got that down and then was able to go off to that. And now she's just working on the chip, getting the chip soldered on. But those are a little different. And so she thinks she fried the chip when she did it. So I just actually bought her a new one today. So, and the other kids are busy doing all the documentation. We're actually they tried to mock it up really quick with the lens and the light to go down. So, well, it's actually a mirror, not a lens, but we'll see. Something else to play with. They were interested in doing the 3D printing on that one. I said, well, let's give it a shot. So they're working away on that one as well. So we'll go through several iterations of that, I'm sure, for the end. So.
And just to jog my memory, Bridget is doing a microphone.
Bridget, we haven't got, before we do the microphone, she's working now on the BME 688, which does ozone and the sulfur gases and volatile carbons, all of that. It's really upgraded environmental chip, which we can also plug into the data afterwards into AI, and then it will sort out the stuff for us. So
the updated SA Cup payload.
Hi, this is Jake. We've been working on the payload for our Spaceport America Cup rocket. So the payload that we're sending you guys at the end of the summer is going to be almost identical to that. So we're going to get a really good test. Pretty much everything is done. We just have to fully assemble it. That gets launched mid-June. And then, any results that we get there, any changes that need to be made, we'll make those. But things are looking good. We've got a lot of the environmental sensors. Drill, what sensors do we have on there?
We've got acceleration, a gyro, I think some temperature sensor. Yeah, pressure. The GPS we couldn't get to work, but not many. I think that no one has been able to get that to work yet. So
yeah, I've been using it. It's I think that's important is that they understand that you connect to it using I2C.
Okay.
Domain4.com /INA.
IN as in navigation.
Yeah.
Okay.
Yeah. So scroll down there. So you can see there's a library here and some an Arduino library here as a test.
Yeah.
Yeah. Double click on that. And
okay, and then there's one example here.
Yeah, click on that. So there is a way to access a GPS. So what I suggest is that I'll use that example, but remember that normally with the GPS, you access that using a UART serial port. But because ours is connected as like our sensors, then you have to connect to it over. I2C. So that's actually what this example here shows. So what I suggest, just go in and start it here, domino4.com /INA, or go into GitHub onto our Domino.com site and then find the RNA chip. So there's some documentation there. So that's how I read it. But this is a GPS I assume they also have. And on the back of the chip, there is like some solder point here. And if they solder in, let me put it here. If these are soldered like this one here is, then it has activated the serial port. And they're normally not soldered. And if they're not soldered, which is the normal way they are operating, then when you click it into the circuit, then you can program and things like that. But if they are soldered, they've override the serial port, which is used by the PPU. So when you program it, then the GPS will disturb it. So what you have to do is you have to take the GPS out, program your board, put the GPS back again. But then when you take this out, of course, then you don't have serial communication to your device. So you can't use it to prototype, all that kind of stuff. So that's the reason why we configured it. So we put some other firmware on it. And these solder points are not soldered. And then you can use it I2C. You can use it in I2C even if they are soldered, but then it just messes up your ability to use your PPU. So yeah, it works fine. There's a little LED that's green. When you plug it in, you should get some power. So I'm just gonna demonstrate that without any call, but just to show you. So if you, here I have the PPU, and if you plug it in, you get like a green light. You can see here, there's this green light here. And when that starts flashing, you got a signal. So obviously this thing is not going to work because there's, I mean, it could give a signal if it's outside. But the thing is that it's steady green when there's no signal, and they start blinking if there's a signal. So yeah, that's how it is.
One question. How long has it taken you to like get a fix when you've used the GPS? Because for us, we've left it outside for like 10 minutes and it still hasn't gotten a fix.
Okay, so it can take some time to get a fix. It's basically the well, in this case with this thing here. So you can see on the back of the chip here, there's like a solder thing here for a battery, which we haven't mounted on this thing here. So the way it works is that it has to download the almanac every time you power it on. And that's the reason why it can take some time to get the fix. So if you have 180-degree free sky, and many times the people put it outside, they put it outside the window, and then of course they don't have 180-degree, they have 90-degree or whatever. You only have, the half of your horizon is blocked by the house you have. So when you put it outside, I want to test this thing here. If you want to get a good idea about how long time it takes, then just make sure you have a horizon all the way around that is available. Of course, that makes it like difficult to test if you have to sit with a computer in your classroom and then have this thing here hanging outside. But what I have done is that, I put something on and then Wi-Fi, and then I check it over Wi-Fi how it works. So I connect to it over Wi-Fi. And then I just put in a power bank and test it outside. What I normally do when I tested this thing here, I haven't used it for the last some months, but last time I did it, I probably was like, 30 feet away from the house, 2 stories. So, then I had a fairly open sky, and then I get a signal like 5-10 minutes. It can take like 15-20 minutes. And the reason for that is that what happens is that you have to download this almanac from the satellites, and they keep sending the almanac down. And if you miss a record, then you have to wait till that record has been sent again. So that's the reason why sometimes it can be quick. It can take 2 minutes if you have a good signal, and sometimes it can take like 10 maybe in 20 minutes if you have a bad location or not free sky. But try, just take it out and see if you can see the green light changes color before you maybe play with the communication. Then you have an idea if you get the signal or not getting the signal.
The GPS chip, we were going to use that as well on the outside of the packet. Well, not the outside, but closest to the open area. But if it has problems getting the fix, I wonder how long, within the packet payload itself, how long will it take to get the fix? Or is that something we're going to have to adjust for? I guess Bjarke will find out when he puts it together.
Okay,
yeah,
so Bjarke, if I can just answer this very quickly. Sorry, Jim, what it is that Jarell and the team, they want to use the GPS when they do their rocket so that they can recover their rocket and they can get the altitude. So they're not necessarily going to use the GPS on the high altitude balloon project.
Okay.
Because we haven't actually applied for that with NASA. And we know that since they're going to recover everything, we didn't necessarily see the necessity to have the GPS on that.
Okay.
So it's going to be a nice to have. It's going to be a nice to have, not a need to have. Sorry, Bjarke, back to you.
Right.
Yeah, so I just want to say that my plan is to talk to them about whether I can put a GPS on or not. And if I can, my consideration is that using the CAN bus, this communication here, the only thing I really just want to make sure of is that we can synchronize our clock. So my idea is that I do some kind of like module where I can synchronize the clock, and then you record your data with the clock. I record my data with the clock, and I would then have I would hopefully have a GPS or something else, because I maybe put like another GPS on just to see, something with a patch antenna or something with a better antenna if it is. And maybe it kind of like sits like, so it has a better visibility. I haven't seen how the installation of this thing here is. So I don't know if, if we are in a closure that's like works as a Faraday cage or whatever. So I'm definitely not going to guarantee that we have a GPS signal. But if it was, then I was going to record that with my other data, and then I'm going to share that, and then you can match that up with the time, so we have the same clock. So whenever you record something, you could see exactly where, when, and other stuff happened. So that's kind of like my plan to do it that way. So you record your data, and then you pair it with our data afterwards.
Very good.